All right. So I am going to take a couple notes right here. Just gonna say they are to dos. Um, One thing I want to do is get arrow keys working, so we don't need to switch to typing mode. Maybe that's a bad idea. Maybe we want typing mode anyway, but I think it would be nice to just have arrow keys. Another thing to do, I'll put it right here, to do handle delete or backspace, really. Although we want to handle delete, I guess, also. And just other, random characters, things like that. Uh, doo, doo, doo. So, what we can do now is look at a way uh, to go ahead and clear the input in a nice way, so that we don't have to do this printf every time. So what I want to do is introduce a function. So first of all, we'll need this. We'll need to include this file. It's going to be standard lib.h. I spelled include wrong. Go ahead and put that up at the top. All right. So what this is going to do is give us a function. We can go ahead and look at it here. I'll type man memset. So it fills a memory with a constant byte. So this is very useful because we have this collection of memory, this input right here, and we want to go ahead and fill it all with the same size, right? So what we are going to do is say memset. We'll pass it in input. Let's see, where does it show? Yeah, so right here, the description. It fills the first in bytes, and you see in is going to be the third thing, of memory pointed to by S, and that pointed to we'll get to in just a second, with a constant byte C. So, to say input, we are going to say 0, and then we are going to say 256, right? Now, keep in mind, let's say that we had something like int nums of 256, right? And then we wanted to set them all to 10, or let's just say we wanted to set them all to like -1, right? If we did 256 here, that would actually be wrong, right? Because if we read the description, it says it fills the first in bytes. So if we have nums, which is 256 ints, and that's 4 bytes per integer, and we only set the first 256 bytes, we would run into trouble, right? So what we could do is say, use this operator, size of. So it's pretty much, it's an operator just like plus or equals or multiplication is. It's kind of weird that it looks like a function, so don't really worry about the difference. Just want to make sure the terminology is clear. We could say size of int, which is always going to give us the number of bytes of the type on the computer that we're running. So, if we compile this on a computer where, let's say, int was 16 bits or only 2 bytes, then luckily for us, size of int would give us 2 instead of 4. So yeah, keep in mind size of is giving us it in bytes, not bits. So we can do this. Now, you might be thinking, well, why don't I just say times 4? Because I know I'm running it on my computer, and I know that on my computer an int is 4 bytes. And, well, technically you can do that. It's usually nice. I mean, part of it is just it's more robust to do it the other way, right? Because you don't know if you're always going to use the same computer forever. Another reason to do it is just that it's way clearer right here that we're we're multiplying it by the size of something. If you just have 256 times 4, you might look at that later and be like, wait, why am I multiplying this by 4? That doesn't, like, that seems wrong, or maybe that's a typo, or why don't I just multiply by 8 instead, right? And, we could see we would get into lots of trouble doing that. So, in fact, just for my own personal style, even when I'm dealing with bytes with chars, I'll just go ahead and multiply it by the size of char, right? Which is going to be 1, so it's going to be equivalent, right? And I do that just because it helps with my sanity, right? I mean, it tells me when I'm reading this that I'm sort of expecting this 256 is representing bytes, right? I care about it in terms of bytes. It also just, it's just kind of a general paranoia thing that I do. You don't have to do it. Just thought I'd mention it. So we'll go ahead and get rid of those numbers again because we don't need them. What I am going to do now, though, is we are going to do a memset on input of 0 of 256 times size of bytes. Sorry, size of char. Size of bytes doesn't really make sense, does it? And now, what this is going to do is every time we start getting new input, every time we go back through our loop, we'll render and then we'll start getting input. Then we're going to just clear out input. So we don't care what was in there before. We are just going to look at it brand new. What did I do? Oh, memset isn't in standard lib. My bad. Memset is in string.h. Oops, I don't want to look at the documentation again. Although, actually, I guess I can, and I can show you right here. It says the file, the header file that you'll use to include it. So anytime if you see a function, like if you're Googling around or something and you see a function, you're like, oh, hey, that's really cool. I could use that. You can just go ahead and look it up in the man pages, and it'll show you, hey, you need this header file, right? It gets to a point where you've included enough header files that most of the things you're going to want to use have already been in one of the header files you included. But it's just nice to always, know that you can fall back on that. All right, so let's do typing mode. Say the cat jumped high and slept on the desk, which is where my cat is right now. Go ahead and see. There she is. She's sleepy. Then I can type the dog jumped on the bed. And you can see now, we're working using this printf, right? Using this very succinct sort of style. And the reason is because printf, it's going to look at input and just stop when it gets to the first 0. And now we have made sure that everything is 0, and we're just going to start filling it up from the beginning, right? So that is very good, very helpful, very useful. Okay, so now that we are doing that, I guess I can go ahead and turn this back on because we might want to change modes every once in a while. And compile. Hello. Byte. And now we're back in normal mode. Okay, cool. And I can go back and say hello again. Like that. Okay, cool. All right. So, probably. Well, again, let's just look over the code and see some of the stuff that we could be doing, maybe improving. Again, we still have this draw level problem where maybe we want a nicer way to do that. We could be doing these to-dos, but maybe we don't really feel like it right now because our game isn't doing anything cool. So do we really want to be spending the time getting like arrow keys to work? Because we're not going to be able to do anything new with that, right? We're still just going to be kind of bored and, want to work on our game more. Um, we have these numbers right here. These 20 and 10, and we're using 20 and 10 down here again. And we're also doing the same thing now with 256, right? So we have 256 here, here, and then in the other memset, right? So that is an area where we might want to start turning those into variables, right? So you can imagine a case where later on in the game, let's say we do want the player to be able to type more than 256 characters. Well, now we're in an issue where we just say, oh, cool, we'll do 512, no problem. And then we see this one right here. We're like, oh, yeah, 512, that's cool. We'll do that. Nothing bad will ever happen to us, right? Except we forgot that we had a 256 down here, right? Which is going to be a load of unhappiness for us. So what I am going to do then is define a couple of macros, is what they're called. And so this will be a new concept. It's very simple. It's actually probably like the simplest thing in the world, but it can just kind of look weird if you're not used to it. And you might be wondering, why would we even do it this way? And I can explain that in a second. So I'm going to say pound define. You notice it's the same sort of like pound key syntax that we have there. And what I'm going to do is type this all in all caps. You don't have to use all caps. This is just my personal style. So anytime I see something that's all caps, I know like, oh, hey, this is a macro. Input char count. It will do max input char count. I'll say 256. And now I can say max input char count. Let's go ahead and max input char count. Go ahead and replace that there. And then I'll go ahead and replace it here, right? All right, so you might be wondering, hey, that's a number. Why didn't you just type a number? And that is a very good question. The reason I didn't type a number is that when our program is compiled, what the macro does is when the compiler is going through and looking at the code, we've just told the compiler, hey, every time you see the words max input char count, literally just replace those characters with the characters 256. So it's going to do this pass at the beginning of the program where it's going to read everything. It's going to look for all the macros. It's going to change the characters. And then it's going to compile it and convert it into machine code. Whereas if I type something like this where I said max input count equals 256 and then, type that in everywhere, what will actually happen, what will actually have to happen is the program won't know the size of input until the program is actually running, right? Because it's going to have to compile the program, find, hey, I made a variable called max input count, and the value of that integer is 256 in binary. Now go ahead and when you look at input, go ahead and find out what the value of max input count is, and go ahead and allocate that much space, that many bytes for input. And, et cetera, et cetera. Which is fine on some computers. The compiler can go ahead and do that for you. It can't necessarily do that for you on all computers for various complicated reasons of laziness and technicalities and stuff. But it's just more, it's a little more efficient, and it's just giving the computer more information ahead of time, right? Where it's saying like, hey, we don't need you to compile the program and find out what this number is. We just want you to go ahead and, replace these characters with these characters and, go ahead and know ahead of time the size of our input. So, anytime you see this define thing, right? In fact, we could even do something like this, right? Where we could say define SQ, and it's going to take an X, and it's going to return X times X, right? Well, so what that'll do is anytime I type SQ4, what this is just going to do is it's going to replace it with X times X, right? And here I'm passing in 4 as the X, and so it's going to do that, right? So we can do just simple textual replacements like that. Now, it doesn't work. It's not as powerful as functions because, again, all it's doing is just very simple replacing text with other text, right? So if you want to do more complicated things, don't use macros. In fact, don't even use macros necessarily if you want to do a simple thing. A lot of times a function can be better. But in this case, it's nice because we're not making the computer do extra work. Like, for instance, on Windows, this wouldn't work if I just wanted to use a variable here, like I had, max input defined as an int that's 256. Windows would complain. It would say, hey, we were trying to compile the program, but we don't know the size of this variable yet, and we're trying to allocate space for input. So, yeah. Sorry if that is annoying or confusing at all. You can go and play around with it a little bit. Ask me any questions that you might have. Okay, the cat was lazy. Cool. So, I mean, it looks like we actually kind of are handling the backspace, which is nice. So maybe we're already doing this. It might be something that in getchar is doing for us. I wasn't sure because I haven't really played around with getchar a whole lot. But it looks like that's working, so maybe we are all good. Okay. Oh yeah. Another thing to do is this 20 and 10. So let's go ahead and now here we can go ahead and do this with integers, right? We can just go ahead and say int screen width is going to be, well, let's call it, I don't know, grid width and grid height, right? I'll do 10 for that. So here it's totally fine to use integers because we aren't asking the computer to reserve any bytes of memory for us, right? So we can go ahead and compile that, and you see we are all good. And so now we only have one place to change it, right? If we just say, we want to make a really fiddly change, we're like, hey, I want 22 instead. You see, we're a little wider. We didn't have to do anything crazy, right? All right. I'm going to also go ahead and say, I'm going to do this this printf right here. Oh, well, okay, this is actually kind of interesting. I want to say it's going to be after we draw the whole board. I want to do, if we are in typing mode, I want to say printf that, right? So let's go ahead into typing mode. You see we have oops, again, some garbage. That's just from me pressing the arrow keys, which aren't really letters in the way that char is. The cat slept like that. Okay, cool. And so now we have like a very clear. We got to have a lot of things going on, right? The border of the window has changed. We say that we're in typing mode, and we have this little prompt asking us to type in characters, right? So that is pretty cool. All right, so now what I want to do is get just a really simple interaction going with this thing. So what I want to do is check to see if you go up to the creature and you go into typing mode and you type attack, I want something to happen, right? Maybe, later on in the game, we'll have more complicated things, like maybe you have to have a sword to attack, you have to, check your inventory or whatever. Um, and, that could actually be pretty cool, having an inventory of words. I'm going to take a little note of that. Inventory of words. I keep thinking of Pokemon when I'm thinking of this, like, words or Pokemon. You're going around collecting words, something like that. That could be interesting. Um, but yeah, so I want to go ahead and say that if you go up to, if you type attack, you're going to, like, hit the creature, right? So let's go ahead and do that. Let's see. It's a good way to do this. Yeah, okay. So, yeah, this is what I'm looking for, this printf. Which, honestly, we probably don't need that printf, right? Because you just typed out the input. We don't need to see the input again. It's a little redundant. But right here, I want to see... All right. If you type out attack, we should attack the creature. All right. So what we want then is a way to take this input, this array of characters that we have, right? And we want to go ahead and see if it equals a certain word that we are typing, right? So let's go ahead and we'll just do this the most straightforward way, and then we can go ahead and make it a function and make it kind of nicer, which will introduce us to the concept of pointers and pointing at memory, which you saw at in Memset. Maybe you made a note, or you've just been thinking about it since and going like, why won't he talk about pointers? Well, it's because I'm going to get to it in just a second. So here we will want to do our for loop, right? We're going to say, all right, while it's less than input index, going to do I++, right? Now, what we want to go ahead and do is say, all right, we want to see if input of I equals something, right? Then, we can move on to the next character, right? Well, what we can do here is we can make an array. And we could call it, I don't know, we'll call it attack. And I don't know how many, that's 6 letters, right? We'd do that. We'd say, all right, attack 0 equals A. Then that's going to be T, etc., right? Okay, all right. All right, so that is fine, but you can see that that might get really, really annoying, right? So what we're going to want to do is look at a better way to input that information, right? For right now, what we can do is just say, we're going to have a bool that's going to say that it matches, right? And we're going to say, by default, we're just going to assume that it does match, right? Then we're going to loop over each of these things, right? And we're going to say, hey, if they're equal, then we're going to say, well, really, actually, what we care about is we just say, hey, if they aren't equal, then we're going to say matches equals false, right? Otherwise, matches remains true. We keep going until we get to the end of the input, and everything's good, right? Then I'm going to say, we're just going to print a message, right? We are going to say that you attacked the creature successfully. All right, so let's go ahead and run the game. I'm going to go into this mode. I'm going to say attack. You attacked the creature successfully. Cool. What if I say attack? Well, what if I just spell it completely wrong like that, right? Oh, huh. It still says I attacked the creature successfully. That's kind of weird. What if I say do not? So there's no A's in it. Okay. Oh, well, yeah. I know what that is. Oops. We want to say if matches, right? Obviously. We only want to print that if you did successfully attack the creature, right? All right. Attack a cat, then, we don't attack the creature in that case, right? Okay, cool. So, what we can do then is, let's check this. If I say attack, like that. Well, okay. So that's kind of weird. I typed out a word that has attack in it, and we still attack the creature, right? Or if I say cat attack, like that. Well, okay, so that doesn't work, luckily. So part of the problem is that we're only checking the first in letters of the array, right? So if I say attack the guy like that, well, okay, so now we aren't matching anymore, right? So part of the problem is the fact that attack and our input can be different lengths, right? We know that this word is always just 6 characters, right? But our input could be any number of characters. It can have spaces in it, etc. So I guess first thing we want to do is just say, all right, hey, if the input index equals 6, then we'll do this, right? Otherwise, we aren't even going to bother because we know that they can't be equal, right? All right, so attack. Okay, so that still works. Attack. Well, okay, so that doesn't work, right? Well, that is all well and good then. So what we have here is we have what's looking to us like a function, right? Where it can go ahead and it can take in an array of characters, like our input right here, and it can go ahead and take in another array of characters. It can go ahead and search over them to see if they're equal to each other. And if they are equal, it's going to return true. And if they aren't equal, then it's going to return false, right? So let's go ahead and write that function right after I introduce this idea. So I'm going to delete this, and I'm going to show you what a pointer is, which is this weird looking thing that I just did. So let's go ahead and make sure, see if this works. Like that. Okay. Interesting. So what this symbol, this asterisk, and keep in mind the asterisk can go either place. It's really up to you, whichever way you prefer. I just kind of out of habit do this. You can do this. They're the same. It's kind of weird that you're able to do this, and I'll explain why in just a second. So we know from our first lecture about like what a computer is, how it works, right? That a computer is storing a bunch of things in memory, right? And you can access that memory by looking at addresses, right? This is essentially exactly the same thing that we're doing with arrays, right? Where an array right here, we have 256 bytes, and we can say, hey, we store all of those in one big chunk, right, of 256 things, and we're saying, hey, give me the first one, give me the second one, the third one, the fourth one, etc., all the way to 256. And, we saw the same thing if we had an integer, right? So, in that case, we're going to be storing 4 times as many bytes as we have things, because each of those things is 4 bytes long. So we're going to say, hey, give me the first 4 bytes, give me the next 4 bytes, the third, fourth bytes, etc., etc. So what this is doing is saying that we have this right here, I'll just type it out right here. This is saying, hey, this isn't a char. This is a char star. Or this is an int star. Or this is a, well, I guess those are really the only types we've looked at. Well, no, because, we made our own types. We'd say, hey, this is a position char, right? And what that's doing is saying that this is the address of where something of type char is stored, right? So we can go ahead and actually go ahead and bring this up right here. So I'll go ahead and do that. We can compile our program. And we'll just do kind of what we did earlier, where we're going to go ahead and print things out, just right before we start actually running our game. So what I want to do is go ahead and print this as a string, right? So whenever I say string, a string and a char star are exactly the same thing, right? And they're kind of equal to a char, letters, right? Like an array of characters. So let's go ahead and run this, and you see I'm printing out attack, right? So that's cool. What if I just go ahead and print it out as a number? Might sound kind of weird. Well, okay, so that time it was negative something, right? Now it's, we can see the numbers changing every time, right? Well, okay, that's maybe confusing. That's maybe not helping us. What if I go ahead and print it out as a, oops, keep pressing the wrong thing, as a hexadecimal number? This should, yeah. So, and we can go ahead and run it, and we see that number does keep changing. But what this is saying is, well, first of all, let me just explain briefly what a hexadecimal number is. So just like we have binary, right, which is zeros and ones, we can have hexadecimal, which is going to be 0 through 9, then A, B, C, D, F, right? So we have 10 numerical characters and then 5 letter characters, right? And so that means, in hexadecimal, we have 0, which is 0. We have 9, which is 9. We have 5, which is 5. But then we have A, which is 10. We have B, which is 11. C, which is 12. D, which is 13. E, which is 14. And F, which is 16. What's nice about this is it lets us represent all of the numbers that a byte can represent, which would be 0 through 255, as just two digits, right? So if we go ahead and write something like FF, keep in mind this is 16. Or sorry, I skipped one. This is 15 15s, right? And then this is going to be 15 ones, right? Again, it's just like, if we have 99, we're going to have 9 10s, which I just realized I wrote that the wrong way. So again, 15 16s, we have 9 10s and 9 1s, right? Well, this is the same thing, just with hexadecimal. So if I pull up the calculator right here. We can say, well, 15 times 16 is 240, plus 15 times 1, which is just 15, is 255, which is the maximum value that a byte can be, right? Because again, it's going to be 0 to 255. If we just take 2 and raise it to the 8th power, because again, a byte is 8 bits, then we're going to get 256. But again, we're going to subtract 1 from that because we need to be able to represent 0. So the maximum positive value that it can be is 255. So we are now looking at these hex numbers, right? And these hex numbers are representing the address in RAM of where our word attack is stored. So that's what we mean by a pointer. A pointer is giving us an address to the location of something in memory. So you can see if we go ahead and look at our function right here, this function square, which is going to take an integer x, and it's going to return x times x, right? But it's never actually changing the value of what x is, right? All it's doing is saying, hey, here's a value. Go ahead and multiply that value times itself, right? But what if we wanted a function that squares a number and actually changes the value of that number itself, right? Well, I mean, one thing we could do is just say x equals 4, and then we could say x equals square of x, right? Which would, of course, now set x equal to 16. So that is one totally valid way to do it. When you're dealing with numbers or something mathematical, oftentimes that's a pretty good way to do it, right? But we can go ahead and look at an example of this. And I don't know, I'll call this one square pointer, PTR for pointer. So right here, again, we have this syntax. And again, I'll just show it both ways. So we're saying, hey, this thing isn't taking an x, an integer x. It's taking the address of where an integer x is stored, right? And in fact, this can actually just be void. We don't need this function to return anything, right? All it's going to do is change whatever is stored at this address of x, right? So right now, I can go ahead and say we have an int x equals 4. And I'm going to call this square pointer x, right? Let's go ahead and compile. Make sure. Oh, yeah. Sorry. So if you notice, this x is an integer, right? But what I want to do is look at it as if I want to get the address of it. So that's what this ampersand object, or this ampersand operator, is doing. It's saying, hey, give me a variable, give me something, and I'll go ahead and give you the address of where this thing is stored in memory. So if we go ahead and do a printf like this, we're going to say x is equal to, in fact, I'll just write it like this, at address and stored at address like this. So I'll first pass in an x, which is going to be the value of x. And then I'll go ahead and pass in the address of x. In fact, I'll just comment that out right now. We can just look at this printf. So again, I forgot my new lines, and I'm sad because it's hard to read. So x is 4, and it's stored at address 7C588944, right? And, we can run this program again. And you see now we're stored at 662BEA04, right? And remember, you could go ahead and you could convert this hexadecimal number to decimal, which would, again, tell you the actual byte in RAM that this number is stored at. It's just that number can be very big. It's sometimes easier to just go ahead and print it as a hexadecimal number. Because, again, we don't really care the actual byte that it's stored in. We just want, our program might care, but we don't care if it's stored at byte 10,000 or byte 10 million. That's not interesting to us, from a user perspective of programming. We just want to know what the address actually is. We don't care what that number is. So this is saying that, hey, we made an integer x. It's 4 bytes. We set the value to be 4 bytes. And now what we are doing is saying that if we go to that address, what we will find starting at this address 662BEA04, we will find 4 bytes. And those 4 bytes will have the value of 4, right? So that is kind of useful. It means that we can go ahead and store, instead of actually storing the value of things, we can go ahead and store the address of things. And that lets us do things like, hey, here's an address of something that I might have set in my program, hours ago. Like if it's a game, it could have happened a long time ago. It could have happened when they pressed start on the controller at the very beginning. And you want to just store the address and, pass it along to things. And then when anything needs the actual value, it can go ahead and look up something at that address, right? So before we return to our square pointer function, I just want to go ahead and show you another example of something. So let's go ahead and say that we have a pointer like this, right? And we are going to say that it equals null. And by null, we just mean 0. We mean it's an invalid address. Nothing can be stored at address null or at address 0. It's essentially meaning, hey, we don't have something, like this is an invalid address. Nothing can be stored here. You are pointing to something that doesn't exist. So now we're going to say that the address of xputter is, and we're going to do that %x thing, right? And we'll run the game. Okay, so the address of xputter is 0, right? Now let's go ahead and say that the value of xputter is actually equal to the address of x. So here we see x is 4, and it's stored at this address. And now we see the address of xputter is the same thing, right? So we can go ahead and look at that and say, hey, well, what if I say that xputter now equals 16? And you'll notice I use this star syntax right here. So this is what's known as a dereference. And what that is saying, and it's different than the star right here. So this star and the type is saying, hey, this is a pointer to something. What this operator is doing, this star right here, and this is one of the reasons pointers can be very confusing. So don't worry if this is overwhelming or freaking you out. Like, this would be several weeks of a college level course, and it wouldn't even be your first college level course. So don't worry about this being confusing. I'm just trying to get through all of the information. You'll have something to look back on anytime you're confused. So this dereference operator, what this is saying is, hey, take an address, and I want you to give me the value of what is at that address, right? So I'm going to go ahead and move this down right here, and we can say printf, now the value of x equals, and we'll just go ahead and print x, right? And, we can place bets for what we think is going to happen. But we see right now, all right, so x equals 4, and it's stored at this address, 7b, blah, 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 c3. And the address of xputter is pointing to the same thing. It is pointing to where x is stored. And what we're saying now with this dereference is, hey, go ahead and look up the thing at this address, And I want you to set the value of what's stored there to be this new value. This, now we want it to be 16, right? And now we see that the value of x that's stored at this address is no longer 4, it's now 16. Now, that would be no different, really, than if we just said x equals 16, right? Like, if we just went ahead and did that, well, same thing, right? So this is kind of a contrived example, but we will start to see more interesting ways that this can be used, right? Right now, I'm going to show you how it can be used with this function, right? So using what we did before, we can say, all right, let's set this value. Let's set x to be equal to, and again, part of the reason I picked this example is it's going to look weird syntactically. We're going to say, hey, take whatever is at this address x, because again, we're taking an address, and dereference it to get that value, multiply that value times dereferencing it to get the value again, right? So you see, we kind of have asterisk soup right here. We go ahead and compile it, make sure nothing, terrible and weird happened. So what this is saying is, all right, take the address of x. I want you to take the value of whatever is there, and I want you to set it equal to the value of whatever is there times the value of whatever is there, right? And so we can see if we do this right here, we can compile, we can run it, and we see now x equals 16. Same thing as before, again, so the end result isn't different, but the way that we did it was very different, right? So what's pretty cool about this is now we can start passing in arrays of things into functions, right? So far, we've only seen a way to pass in a single value, right? But we want to do our string equals like we have down here, where we're checking these strings and comparing them to each other, right? We want to go ahead and pass in arrays of things, collections of bytes, and we want to be able to do things to those bytes and, and check their equality, change their value, whatever. But until now, we haven't known how to do that because we haven't been able to pass in arrays. And since arrays are just collections of memory that start at an address, we can go ahead and do that by passing in an address, right? So let's go ahead up here. We're going to say bool string equals, right? And so what this is going to do is we are going to pass in char string a, and let's say we're going to pass in the length of it, right? Because again, when we're dealing with arrays, we care about how long they are, right? We'll just call this len a. And then we're going to say char string b, and we're going to say len b, right? Sorry, we're going to say int len b, right? So first thing we're going to do is we're going to say, hey, if len a does not equal len b, then we are going to return false, right? So that's super easy. We just know, hey, if the two strings aren't the same length, well, they can't be the same string then, right? So you might be thinking, and this would not be a very naive thing to think, that we could just say, hey, string A equals string B, right? Let's just return that. Let's see if they're equal. But remember that these are addresses, right? And the address of where attack is stored is not going to be the same address of where input is stored. I mean, and that's good, right? We don't want it to be the same address. Because if it was the same address when we start typing in input, we would start overwriting the letters in this term attack that we want. And we want this to be constant, right? We want this to be a word we can always look up, right? So what this would do is check to see if the two things are pointing to the same address, right? So what we want to do actually is go ahead and do this for loop, right? Just like we did before, right? And we can say, because again, we checked the lengths. We know that they're the same length. So we can do our for loop, and it doesn't matter. We could use len A or len B. We know that they're the same length, so we're going to look over the same amount of space, right? And we're going to do this I++, and we're going to say, hey, if string A of I, let's return the result. We're going to say matches equals true. We say if string A does not equal string B of I, then we're going to say matches equals false, right? And then at the end, we're going to return matches, right? And in fact, actually, what we can do, we can use this thing called a break. I always forget if I've shown this before. I know we went over it in class the other day, but I forget if I've shown it on the video. What break does is just say, hey, look at the for loop or the loop that I'm inside and just quit doing it. Immediately leave it, right? Because we know, hey, if we're checking two strings and we ever find a character that isn't equal, we're just done. We don't have to keep looking at the rest of the stuff. They can't ever equal each other now, right? Let's go ahead and make sure that compiles. It does. Wonderful. And we can go ahead and just do something like this. Where are we right here? Yeah, right here. We can say, all right, if string equals of attack, in fact, I'll pass them in different way. We'll say of input and input index, because again, input index is keeping track of how many characters we've printed and which one, or how many characters we've input and which the next one to input is. And then I'll do attack and I'll do 6, right? Again, this is kind of gross that 6 is maybe not necessarily the way that we want to do this, right? Because, what if the length of attack changes? Like, what if we change it to attacks? Something like that. Then I'm going to say, hey, let's do this printf, right? And now we can go ahead and get rid of all of this code. And let's go ahead and compile it and run. All right, so I'm going to say go into input mode. I'm going to say hello. Well, okay, good. We didn't get a false positive, right? What if I say attack? You attacked the creature successfully. All right, cool. So this is, I think, super awesome. Because now we have a way to very easily check to see if two strings are equal. Like you can see this equal where we were checking positions, that's not that big a deal. Like if we had to always type this out, it wouldn't be the end of the world. We could still go about our lives. But if every time we want to check to see if a string is equal, we had to type out all of this, which, it's not even that much, but it's still, I don't know, this is what, like 10 lines of code, 12 lines of code, if, I'd shorten it if I got rid of the new lines or whatever. But it would just be really miserable to type this every time. We would maybe make a mistake, right? Like, what if I accidentally forgot to do the break? Or what if I forgot to compare the lengths, etc., right? So that would be a certain amount of unhappiness that I don't really think we would want to deal with. But now we have this really cool thing where we can go ahead and check string equals and say, hey, we attacked the creature successfully. I think the one other thing that I want to do before ending this video is saying that if the creature, we're just going to say if creature.health is greater than 0, then we print it. And the position is equal. Otherwise, we're just not going to go ahead and print it, right? So we can say, hey, if you attack the creature, we're going to say creature.health minus equals 5, right? So, you got a kind of beefy attack. So, going to go into input mode. I'm going to say attack. All right, I attack the creature. I attack again, and the creature's disappeared. Wonderful. So yeah, this is kind of gross. This isn't how we want to do it. We've just hard-coded it in. We are going to look at, I think, more sophisticated types of things to do in the next few lectures, but I think this is a very good stopping place for now. Again, you know, don't be scared of this pointer idea. I know in this lecture I introduced two huge concepts of arrays and pointers, and we've seen that really they aren't very different, right? Because an array is just it's just an address and a collection of things, and the pointer is just pointing at an address, right? But again, this can be definitely kind of confusing. It can be hard to sort of think in these terms. So if you have any questions, go ahead and ask me. If you want to go ahead and play around with this, I strongly recommend it. You can go ahead and play around with the game code also, but also just go ahead and play around with printing the addresses of things and changing the values. Taking an address with this ampersand, dereferencing an address with the asterisk, making pointers of different types, right? Doing things like that. In fact, actually, this is an important thing to point out. You'll notice, like, this char star, like, I said that this was a string, right? But you could also imagine a situation where we only have a single character, right? We only have something like char C, or, char C equals A, and then I want to say char C putter equals the address of C, right? Well, so this is technically a string, right? Even though it's a single character, which is why we care about passing in the lengths of things, because really there's no great way to distinguish between, hey, if we just have a pointer to a char, how do we know how many bytes to go ahead and read? Do we know if this is 20 characters? Is this 26? Is this the whole alphabet, right? Is it a single character? Is it 4 characters, etc.? So that's one of the reasons that this printf function that I showed you below, when we pass in the input, what it's going to do is it's just going to keep reading values from this pointer until it hits a 0. Because that way we don't have to pass in the length. We just keep going until we have a 0. So we can actually go ahead and write a function that does that real quick. I'm going to call this string length. We're going to say it's going to take a string, and I'm going to say length equals 0, and I'm going to say while the dereferencing of the string. Well, in fact, I'll do it this way. We'll say char C equals that, right? So we're going to dereference. We're going to get the very first value from that string, right? Another way to do that would just be say, hey, string of 0, right? Give me the first thing here. We can kind of see the similarities between an array and a pointer, right? So we're going to say while C does not equal 0, we're going to say length plus plus, and we're going to say C equals string of length, right? And in fact, we could go ahead and replace that right there. We could just say string of length, right? So let's go ahead and actually look at that here. So we have this thing called attack, right? And I want to say printf the length of is that, right? So we're going to say the length of attack is string length, and I'm going to pass an attack, right? I'm going to run that. And we can see the length of attack. Did I do something wrong? Oh, yeah, I did. Where is... Yeah, I want to return the length, right? That's very important. Return the length of attack. I'm surprised the compiler didn't cry at me about that. What on earth is going on? String length. Let's just say int len equals that. This is a super, super weird problem. What if I just say, if I just print len? If I go ahead and print it, do I have something else called len? I don't think so. Let's go ahead and do that. What on earth is happening? Well, okay. So first things first, let's go ahead and print FC right here. So when we get the string length, I want to go ahead and print what the character of it is, right? Okay, so we have attack. Cool. I also want to go ahead and print what the length is at that time, and see if we're doing the weird thing right there. We aren't doing the weird thing right there. Oh, I feel like that should probably go away. It would probably just make our lives easier anyway, though that's obviously not the problem. Sorry about the microphone there. What am I doing? The length, it's still printing it. I'm going to go ahead. Oops. Sorry, oops, yeah, I did that. Let me go ahead and see if there's anything. Printf printing decimal as hex. I've never seen something like this before. And I've printed a lot of things in my life. Okay, what if we get rid of all the other prints? In fact, let's just get rid of everything that's doing something with pointers. Oh, ha! I know what it, wow, okay. That makes sense. I'm feel really silly. Again, twice feeling silly today. We see the length is 6, and then I wasn't doing the new line, so I'm printing out the address of attack. Oh, that's ridiculous. You should usually trust the computer. Don't always trust the computer, but that's a time I probably should have trusted the computer. Again, if you already saw what was happening and you're screaming at your computer, put a new line, then I apologize for wasting your time. So yeah, but luckily for us, we got a cool new function out of it where we go ahead and we can take a string and go ahead and look at the length. So actually, a nice thing about that now is we can go ahead and say string length of attack right here, and that way we should still work. If I say attack, we do attack the creature. I can do it again, and the creature is dead. Cool. But now if I wanted to change this to, I don't know, attack good, right? It's like a puzzle game, and you're supposed to figure out that what you really want to do is attack. And, oh, wow, nothing happened. That's weird. What should I do? I want to attack good. Attack good. And now we kill it, right? So we can go ahead and change the length of this thing, and we're always just computing the length at runtime correctly. I'll go ahead and undo that. Not undo that. And I also want to go ahead and remove the printfs from this. David, get out of the way. I don't know if they can see you or not. You're in my way at least. So again with the arrow keys, attack, attack, cool. Oops, I want to go here, and then Q, and I quit. Cool. I just realized we hadn't tested that. I'm glad it still works. So one more neat thing that I can show you is an equivalent way to do the same thing. So remember I showed you this. I'll go ahead and comment that out. I said that we could do something like this, where you said char c equals dereference of string, right? So the dereference, it's going to get the value of whatever is pointed to. And in this case, since we're a char, the value of the first thing at the address is going to be one char, which is 1 byte. So we're going to get a single character, right? And then I can go ahead and say, hey, while c does not equal 0, go ahead and keep doing this, right? But what I can now do is say that c equals dereference of string plus plus. This should work. I'll go ahead and compile it. I usually don't do things this way because it seems a little weird to me, but yeah, okay, cool. So there's a little weirdness right here, but we should. Let's see. You're saying the length is 7. Why is that the case? Oh. Well, okay. I can go ahead and fix that in just a second after I explain this, because the solution won't make a lot of sense. So remember that a pointer is just a pointer to an address, right? In fact, I can go down here, and we can go ahead and look at this. So if I want to go ahead and print the first, I want to go ahead and print attack, right? And go ahead and do that. And when we run, we see we're printing attack, right? But if I want to go ahead and add something to the value, right? Let's say that I just add 1 to it. Add 1 to the address, which remember is in bytes. So this is like saying take the address and add 1 byte to it. So move 1 byte further. Well, now we have TTACK, so we're missing the first letter, right? If I do something like 3, I can go ahead and, just get the last 3 letters, right? So what's cool about that is that we can go ahead and just increment an address in a very very efficient sort of way, right? So what we can do right here, and you see we're getting 7, so I think there's just something wrong with the math that I'm doing. So let's go ahead and do that again. We're going to start out printing the character and then the length. We'll do a new line just like before. We run that. You see, okay, so we get... oh, yeah, so the issue is that we get this... we start at 0, 1, and then we get the K where it's 6. And then... Let's see. Oh, okay, yeah. We're getting 2 A's. That's the issue, obviously. Yeah, so the reason for that is this right here. Oops. If we do plus plus, don't worry, I'll explain in just a second what that means. So if we do plus plus, so if we do x plus plus like that, what we're doing is saying, let's do int y equals, let's go ahead and write it like this. what y is going to equal is 5, right? Because there's like an order of evaluation here. What this is doing is saying, hey, take int y equals 5. Now add 1 to 5. Now change the value of x, right? So the issue with doing it this way with the string plus plus is we were saying, hey, C equals the first letter. Now C equals the first letter and go ahead and add 1 to the address. But what we want to do with this plus plus is say, all right, hey, C equals add 1 to the address, and now that's going to be equal to C, right? So if we did something like this with y equals plus plus x, we would be saying, hey, y equals add 1 to x, now that's the value, right? So it's just anytime you see people do something like plus plus x, just be aware that it is definitely doing something different. It's still adding 1, but it's doing it in kind of a different order, right? Where it's going to add 1 to x before it looks at the value versus looking at the value and then adding 1 to it. So I'll go ahead and leave both of these up right here. Again, this one might be a little more verbose and maybe, it's a little clearer. Oops. What did I do to make the length? I accidentally deleted the return. So yeah, this one might be more verbose and a little clearer. Again, it's using this array syntax that we've seen already and we're maybe a little more comfortable with. But this is also a pretty useful thing to be able to do, is to be able to take the address of something and add a value to it, right? So I'll go ahead and clean up this code a little bit. In fact, I can just clean up everything right there. And then when we run it, we should just get a nice looking game. Attack. Cool. Killed it. All right. And keep in mind, if you wanted to write it this way, you could go ahead and do it. Because again, that's just kind of specifying the order of operations a little more. You're saying, hey, dereference this thing, but first I want you to add 1 to it, right? Let's see. Another way you could do it is you could just go ahead and completely omit the C. So like if you just said string plus plus like that does not equal 0. Let's go ahead and see what that does. Oops, we'll just go ahead and printf length. Oops, because I want to do a new line, so it's on. And we see, yeah, so we get 6 right here. Whereas if we did the plus plus in this order, like I showed you earlier, then you see we get 5. Now, so let's go ahead and look into that. So the reason is, again, we would be dereferencing string after we added 1 to the address. So we would be skipping over the A, right? Which is, that's no good when you want to count the length of a string. So here, if you were to do it in this style, which is super terse, then you would just go ahead and do dereference of plus plus, add 1 to the length, and as long as that isn't equal to 0, then you can go ahead and continue on counting letters, right? So that is 3 different ways to do the same thing with a pointer, right? And, there are times where you can't do the same thing in all 3 ways. Sometimes it's easier to do things in a certain way. I personally kind of like this syntax the most for like standard things, especially when I'm dealing with something like a string, right? Maybe if I'm doing a more like mathy type of operation, I might use something like this very terse syntax where I'm just adding things to the address. But again, it's kind of up to you, the style that you prefer. And, given the time of the week, you might prefer one style over another. So I want you to go ahead and try experimenting with this pointer thing. And try doing like this syntax. See what happens when you use numbers. Like, does this plus plus, does it increment the byte, or does it increment by the number of elements, right? So if you have an int and if you have an int pointer and if you do a plus plus, is that going to add 1 byte, or is it going to add 4 bytes, right? Is it adding 1 or 4 to it? Because remember, if you have an int pointer and each element is going to be 4 bytes, then you would kind of want the plus plus to add 4 bytes, so you move to the next number, right? But, does it? That's an interesting question. And, in the future, we will see some really crazy cool things with pointers. Like, one of the cool things about pointers, sort of related to the last question that I just posed, is if you have a 4-byte number and you have a pointer to it, what if you want to get the last byte of that number? What if you want to get only the first byte of it? Well, normally that's something you couldn't do if you were looking at it as just a collection of numbers, right? But if you have the address of the number and you know how big it is, you can actually do really cool things where you're like, hey, I want to look at the first bit inside this number. I want to look at the 8th bit inside this number and look at what the value is. And that can be really cool and powerful, though we don't need anything like that right now, certainly. So yeah, I think that'll do it for this week. Just go ahead and let me know if you have any questions, and be proud of yourself if you've gotten to this point in the video and you have even the shreddest sense of what is going on, because this is very complicated, advanced stuff. But it's also very powerful, and it's one of the big reasons to use C as a language. So I thought I would introduce it sooner than later, so you can maybe get comfortable with it for when we start getting to the really crazy things with it.